So far, we have only used digital I/Os. These types of I/Os have only two possible values: 0 or low, and 1 or high. But is it possible to detect more levels? Yes, with analog inputs. There are many signals that have a continuous variation. This means they have infinite possible values. For example, the temperature of a glass with water and ice that we leave seating in the sun on a very hot day. At the very beginning, the temperature is going to be very low. But as time passes, the heat coming from the sun starts melting the ice, and the temperature of the glass is going to increase. After a few minutes, all the ice is gone, and only water at the ambient temperature will remain in the glass. If we are sensing this temperature with a thermocouple, temperature sensor, and we try to plot how the temperature of the glass changed from the very first moment until the end, it looks like this. As we can see, the temperature values have a range defined between T minimum and T maximum. This happens between the initial and final times. The analog inputs are special inputs of the microcontroller, and they are designed for continuous signals. They are the input to a device called analog to digital converter that is inside the microcontroller. The ADC takes the analog signal, the analog voltage which the thermocouple provides by converting the temperature of the glass of water and ice to an electric signal, and converts it to the digital domain so the microcontroller can process the signal and use it for a particular purpose. But how does it work? The ADC discretizes the analog signal. Within a given range, it has several discrete levels. And when it reads the signal from the sensor, it assigns to its output the closest level to the value of this signal. Let's look at it in a graph. We assign the lowest level of temperature we want to measure to the lowest level of the ADC, and the maximum level of temperature to the highest level of the ADC. Then any middle value within Tmin and Tmax directly correlates with one level of the ADC. We assume a linear relationship between the temperature and the sensor reading, which is true for most such sensors. The range of the ADC is defined by the number of bits associated with this peripheral, which in the case of the Arduino Uno board is 10 bits. These bits can be either 0 or 1, and that is why they are called binary. With these bits, the maximum and minimum values we can write with a binary code are like this. The minimum number is equal to 2 to the power of 0 minus 1. This is equal to 0, which is equivalent to 0 volts. The maximum number is equal to 2 to the power of 10 minus 1. This is equal to 1023, which is equivalent to 5 volts, where the 2 comes from the binary representation of the numbers. These maximum and minimum values define the range of this particular ADC with 1,024 different discrete levels. Now, let's go back to the glass of water example. The maximum temperature the glass of water reached under the sun is 30 degrees Celsius, and its initial temperature, or Tmin, was 0 degrees Celsius. Then, when the ADC reads the value 1023, it means the actual temperature of the glass of water is 30 degrees Celsius. When it reads 0, it means that the temperature of the glass is 0 degrees Celsius. But what if the temperature of the glass is 20 degrees? The ADC will read this, which is equal to 682. In the particular case of 26 degrees Celsius, the calculation gives 886.6, which is not an integer. Here, the ADC will assign the closest integer value to 886.6, which is 887. This introduces some error in the measurement, which can be improved with more bits to do the analog to digital conversion for the applications that require higher accuracy of the measurements. Now, let's see what functions we need to know to use the analog inputs in the Arduino Uno board. To read the analog input, we need this. where pin is the analog input selected, and data is where the output value of the ADC will be stored. Having said that, we are ready to build an example on Tinkercad. We select the Arduino Uno board as usual, and here at the bottom we can see the 6 analog inputs it has, from A0 to A5. Now we include a potentiometer, which is a variable resistor. When we hover over the legs of the pot, Tinkercad tells us that the left and right legs are terminals 1 and 2 respectively, and that the middle leg is the wiper. The left and right legs have to be connected to power, 5 volts in this case, and GND either way. However, the middle leg is the one that is used to measure the value of the resistance, and it has to be connected to A0, or any other analog input pin. We select the colors of the traces, and finally, we are ready to write the code. We define the variable pot as A0, and then we define the variable data as a long integer initializing it as 0. We need this variable to store the values we read from the analog input. Then, we define pot as an input. We are going to need the serial monitor, so let's copy the serial begin instruction in the setup part of the code. In the main loop, we have to read the ADC output using analog read. The pin this time will be pot. And we store the values in the variable data. Now let's add the serial print instruction to send the value of data through the serial monitor. Let's run the simulation. We open the serial monitor and we hit Start Simulation. If the wiper blade is at the far right, we see that the value measured by the ADC, data, is 1023. And when we move it to the far left, the value of data is 0. Okay, this looks good. Now we can stop the simulation. It seems that the maximum value of the resistor is 250k ohms, and the minimum is 0. So let's adjust the measurement so the serial monitor displays the right value of the resistance. We hit play. And when data is 0, the new value of data after the calculation is 0. And when data is 1023, the new value of data is 250. Now we can explore another sensor. For instance, we can use the flex sensor. It is a resistor that changes its value when it is bent. Let's connect it to the Arduino board. First, we delete the potentiometer. And then, we connect one of the legs to the GND and the other one to the 5 volts pin through a resistor. This end of the resistor is also connected to the analog input A0. Let's modify the code to make it work in this case. We change the name of the pot by angle to make the code clearer. And for now, we can comment out the conversion of the data. We start the simulation. When the angle is 0 degrees, the raw data is 990. And when the angle is 180 degrees, the raw data is 1017. The linear equation for these 2 points, 990 0D and 1017 180D, is given by this. So we can uncomment this line to transform the raw data to display the actual angle of the flex sensor. We are ready to test the code. Let's hit play. Now we see that the serial monitor displays 0, which is correct because the sensor is not bent. And when we bend it to 180D, we get 180 in the serial monitor.